All right, welcome. Today, we're going to pull back the curtain on C++ and look beyond just the syntax to uncover the hidden story of an object's life.
You know, when you create an object, it feels like a simple, single line of code. But it's so much more than that. It's actually the start of a whole life cycle, a journey that begins with a pretty chaotic birth and ends with a clean, orderly, well, death. So let's start with that chaos.
So you'd think when we create an object, it would be, ready to go. But that's not what happens by default. Not even close.
Imagine we write this super simple line of code, customer C1. Okay, great, we've made an instance of our customer class. But what does it actually hold? Like, what is inside this brand new object right now? Well, the truth is, the object's memory is filled with whatever random, leftover garbage data was already sitting in that spot. So think about it for a second. We have a customer with no real name, some random account number, and a totally nonsensical balance. This isn't just useless. It can be downright dangerous in a real application. This is the chaos we start with. So how do we fix this mess? Luckily, C++ gives us a very special type of function that's designed specifically to bring order to this chaos and give our objects a meaningful, valid start in life. And that solution is the constructor. The most important thing to remember here is that a constructor guarantees every single object starts its life in a predictable, useful way. You can always spot one because it has the exact same name as the class. And here's the unique part. It has no return type. Its only job is to get things set up correctly from the get-go. And this slide just illustrates the difference perfectly. It's night and day, right? On the left, you've got that initial chaos we talked about. But on the right, thanks to a default constructor that we wrote, our object is immediately meaningful. It has a default name, maybe a starting balance of 100. It's a valid usable object from the instant it's created. Okay, but what if we want to create objects with different starting values? I mean, a default customer isn't always what we need. This is where constructors really start to show their true power.
Right. We can't just rely on the same default constructor for every single situation. We absolutely need more flexibility. We need to create unique, fully formed objects right at the moment we declare them.
The way C++ handles this is actually pretty clever. It's called constructor overloading. We can define multiple versions of the constructor, and each one can take different arguments. Maybe one takes just a name, another takes a name and a balance. You get the idea. The compiler is smart enough to just look at how we're creating the object and automatically pick the right constructor to call. It's fantastic.
But this flexibility introduces a classic trap, one that gets a lot of people. What happens if the parameter in our constructor has the same name as a member variable? Like name here. Well, the compiler gets confused. That line, name equals name, it just assigns the parameter to itself. The object's own member variable is never touched.
The solution is this handy little thing called the this pointer. It's a special pointer that, inside a class method, always points to the current object instance. So, by writing this.name, we are explicitly telling the compiler, hey, I'm talking about the member variable called name, and I want to assign the value of the parameter name to it. And just like that, the ambiguity is gone. Problem solved.
Now, this quote really hints at a much deeper purpose for constructors. Their role goes way beyond just setting a few variables. We should really think of them as the complete setup phase for an object's entire life.
And this is why constructors are so critical for writing solid, robust software. They can do all sorts of setup work. They can grab dynamic memory from a big pool of memory called the heap. They can open files or establish network connections. And this is a huge advantage because if a resource isn't available, the object creation fails right away. Instead of letting your program crash halfway through some critical operation, it's all about failing early and safely.
So, we've seen how an object is born and customized. But, every life has to come to an end. And in programming, that end needs to be just as clean and orderly as the beginning.
And for that, we have the destructor. It's the perfect counterpart to the constructor. You can spot it really easily because it has that little tilde symbol, that squiggly line, right before the class name. Its one and only job is cleanup. It's a perfect symmetry, really. They do the exact opposite. If a constructor opened a file, the destructor's job is to close it. If it opened a network connection, the destructor closes it. And most importantly, if it allocated memory, the destructor frees that memory. This is, without a doubt, its most critical job. If you don't release the resources that the constructor required, you get what's called a memory leak. Your program starts using more and more memory over time, like a leaky faucet, until it eventually slows everything down or just crashes. The destructor is what prevents this from happening.
Okay, let's put it all together now. Let's see what happens when we have multiple objects living and dying inside our program.
Now, I want you to pay close attention to the order here. The objects get constructed sequentially, just like you'd expect. C1 is created, then C2, then C3. But now look at the destructor column. They're destroyed in the exact reverse order. C3 goes first, then C2, and finally C1. This is a fundamental principle, and it's known as last in, first out.
So why on earth would it do this? Well, there's a really, really good reason, and it's all about preventing chaos. Imagine that object C3 depended on C2 for something. If we destroyed C2 first, C3 would suddenly be left in a broken, unstable state. This last-in, first-out rule guarantees a safe and orderly shutdown every time. So you see, understanding this constructor-destructor lifecycle isn't just about syntax. It's about writing code that's robust, predictable, and safe. Which leaves you to wonder, what other hidden behaviors are quietly shaping the way your programs run?